Laplacian or GCL and the vector diffusion maps, VDM. And this is something which you may already seen before. Well, something very similar, graph Laplacian. Now we have an added term called connection, and we saw diffusion maps, and we have an added term, vector. These are some selected papers related to this topic, which we will discuss in this series of lectures. And in the end, we will discuss some applications of how to use a graph connection Laplacian and the vector diffusion map. And in the middle, you will see the motivation of this introduction of this model and algorithm. Oh, okay, it's back. So let's talk about the motivation to consider graph connection Laplacian, and later on, the motivation to consider vector diffusion map. So the warm-up example is this set of images. We have some extra information. In what sense? Suppose that now I give you three images, X, Z, and Z. And obviously, our eyes are very good, so we can see, oh, this is Z and that is also Z. But if we just use L2 distance, that is, you just take two images as two functions and calculate their L2 norm of the distance. That is L2 distance. Then you will see that D12, D13, and D23, their distances are all quite big, meaning that they are all different. However, as I mentioned, by our eyes, we know that these two are Z's. So how do we know that? You can see that suppose you rotate Z for a bit to match this Z and compare their different distance. The distance is actually 0. Okay, so, and what is this defined? This is defined in the following way. It's called rotationally invariant distance, RID. What you do is you take one image, II, and you want to compare a distance with an IJ. What you do is you find a rotation and you use a rotation that action on IJ. That is, rotate it a bit and do the comparison, and you find the minimizer over all rotations. And because this is a continuous operator and SO is a compact set, so you can always find minimizer. And this is called Dij, which is a distance, called RID distance. Now you see D tilde 23, as expected, is 0. And D tilde 12 and D tilde 13, they are 59. Good, isn't it? So this suggests us that actually by taking the RID distance, you can somehow group or cluster these three images into two clusters that fulfill our perception. So, you see, in addition to get a distance for the clustering, you also know how you rotate IJ to compare with II so that distance is minimum. So this OIJ, which is about rotation, actually is a free information. This information tells you the relationship in between two images. One natural question we can ask is this useful? Can we use it? And to use it, we give it a name. We say, hey, this OIJ is called connection. And you will see that this connection is directly related to the connection we use in differential geometry when we describe bundle structure. And in this setup, it describes how two images are related. So the general setup we have after this motivation is the following. In general, when we do high-dimensional data analysis, usually what do we have? We have a set of objects or data points. And to do analysis, you need to know how to compare two different objects or two different points. So you need a matrix to define the affinity between pairwise objects. Moreover, sometimes we have non-trivial relationships between pairwise objects. For example, the rotation I showed you in the previous slide. So how can we take all these take these pieces of information together to do some analysis? That would be the question. And in the previous image example, objects are images, the matrix is RID, and there will be some non-trivial connection, a relationship that is a connection, OIJ. And what we want to do is usually find the underlying structure as usual. We want to do classification, we want to do prediction, and there are a lot of missions we want to do. So how to achieve these goals by using this piece of information, in particular, connection. Okay, so the mathematical framework is the following. Now you have a set of objects, I, J, K, etc. And you get information among objects. For example, you have matrix, okay, non-trivial relationship, connection. So what we do is we convert this set of information, pieces of information, into something called connection graph. Connection graph, which is V, vertices, E, edges, W, affinity, G, connection, which is defined in the following way. V is vertices, which is composed of n data points or n objects. In our previous example, that will be a set of images. E is the edges among data points. W is the affinity between data points. This is sometimes called affinity function, which we encountered before in graph Laplacian and diffusion maps. Remember, V, E, W were what we used to define the graph Laplacian and the diffusion maps. Now we have something extra called G, which we call connection function. What is it? It is actually a group valued function defined on the edges. That is, at each edge, we not only have the affinity, which is a positive value, Wij, describing how close two points are. We also have a group function describing the relationship in between two objects. And here, to simplify the discussion, we focus on rotation, UD or OD. It can be more general. It can even consider diffeomorphism as long as it is a group. But yeah, we will see if we will encounter this kind of topics. But UD or OD, they are the most common, at least example in the examples I will show you. And the assumption, we need to put some assumptions. We will make the assumption that the graph is undirected. For example, Wij is Wji. This is something very similar to what we had before, because if Wij is not equivalent to Wji, that is the affinity matrix is not symmetric, and we know that for non-symmetric matrix, there may not have an eigenvalue decomposition. So to simplify the discussion, from now on we'll always assume the graph is symmetric. And also, Gij is equivalent to Gji star. That is, there is a conjugate relationship. If you have a Gij from I to J, then J back to I will be the inverse, or the conjugation, or this is just, well, transpose conjugation, complex conjugation of the matrix, which is the inverse in our set. So that will be the mathematical framework. So now with this graph connection, connection graph, we can define the quantity called graph connection Laplacian, which is a generalization of graph Laplacian. What we do is we construct an n by n block matrix with d by d blocks. That is, S itself is actually an n times d by n times d matrix, but it is actually an n by n block matrix with each block of size d by d. What we do is, for ij's block, this is ij's block, we put Wij, Gij, when ij is in E, or we just put a zero matrix of size d by d if ij is not in E. That is how we construct S matrix. And then we construct a diagonal matrix. This diagonal matrix is a diagonal block matrix such that you have in the diagonal entry, diagonal block entry, it is the summation of all the rows, okay, in all the rows, and you just put it in II's block matrix, where you put Wij summation and then multiply by ID. That is what you construct. D is a block diagonal matrix. And the normalized graph connection Laplacian is defined as identity matrix of size n by d. Identity matrix of size nd by nd subtracted by d minus s. So now let's take a look before we continue. Imagine that Gij is 1. Suppose Gij is 1, just 1. Okay? Then you see S matrix is reduced to W matrix we had before in the diffusion map, right? And then this guy is reduced to the graph Laplacian. And we will see something, see another picture in the next slide. But before that, we made some assumption that is D, this D matrix is actually not degenerate. This is the same assumption we made before when we consider graph Laplacian. Otherwise, if it is degenerate, then how can you define D inverse, right? It's a very simple assumption. Then this is what I mentioned about relationship with graph Laplacian. Suppose Gij is 1. All Gij is 1. Every Gij is 1. And what is 1? Just remember by definition, SO1 is just identity. Okay, so what do we say is when the group relationship is trivial, totally trivial, just 1, then we just get a graph Laplacian. And the graph Laplacian will describe the random work on the graph. That is D inverse W, right, will be the random work on the graph. So that is a relationship with graph Laplacian. But in general, we have a group relationship, which makes things more complicated. Okay, so there are some basic properties of graph connection Laplacian, and as what you can do is you have, for example, a V, which is an n by d matrix vector, and for a vector of size n d, sorry, not n by d, n times d. For a vector of size n d, you can view it as a block vector of size n with the block size d, right? So you have a vector of size nd as a block vector, with each block d. If I draw a picture here, it is like this guy. This is v. This is size nd, and you have this is d by 1, d by 1, and that in total n blocks. Okay, so this guy is a size n by d. Sorry, size nd, and each block size is d by 1. Okay, so that is what I meant by v. Now, you have D inverse S, and D inverse S is a block matrix of size n by n with the block size d by d. What you do is you can multiply D inverse S by v and evaluate at the ith block, and that can be written on the right hand side. It becomes Wij, Gij, V, and you consider jth entry. So the notation I use here is this guy is denoted as V2. This means the second block. Okay, if I use this notation, then you see you have a jth block and multiplied by Gij and weighted by Wij. And this is the normalization. That's what you have immediately. What you can see here is this guy, Wij divided by the row sum of Wij. This guy actually is a probability, which describes how you jump from J to I. So, you can just view it as a vector value status on the vertices. That is, you have status, and the status is described by a vector. And when you compare different status, or you do random work on the vertices, what you do is you take the vector and you apply the connection before you compare with other blocks. That is what you do here. And here's a pictorial picture visualization. At each vector, at each vertex, you have one vector. These are vectors. And when you want to compare Vj with Vi, what you do is you multiply Gij by Vj before you compare with Vi. And here the notation is a bit inconsistent. This Vj should be V bracket J, and this is V bracket I. Okay, hopefully this is clear. So this is what this picture, this is what this equation is describing in this picture. And there are some basic properties, some more basic properties. For example, what you can see is, because S, you can define, because we consider D inverse S. And D inverse S in general is not symmetric. But D inverse S is similar to D minus half S D minus half, right? And this guy is symmetric. So what you can do is you can do eigenvalue decomposition of S tilde and multiply by D minus half back to get eigen decomposition of D inverse S. This is exactly the same thing as we did before in graph Laplacian. So you can find all the eigenvalues and eigenvectors from S tilde. And now if you order lambda J, the eigenvalues, such that it is in a decreasing order, and what you can prove is lambda I will always be bounded by 1, and then this can be proved directly by using the spectral norm is always bounded by L infinity norm, the same trick as we did before. Then what you have is V transpose I plus minus S tilde V is, this guy is always positive. Okay, so that is somehow another way you can prove this lambda I is bounded by 1. So that is a kind of an immediate quantity that you can play with. So if you do the ordering, no matter what you do, you always have this result. So there are several ways you can prove it. Okay, very good. So these are basic properties of graph connection Laplacian, and we will have more to discuss later. But let's talk about vector diffusion maps and what is it. What you do is do some very basic observation. You have S tilde, and what is S tilde? If you remember, S tilde is D minus half S D minus half. So it's a symmetric matrix. And if you evaluate its Hilbert-Schmidt's norm of the ij's block square, you get a trace of S tilde raised to power 2t ij S tilde 2t S ij transpose. That's what you can get immediately. Okay, and the t is a real number, positive real number, which is will be interpreted as diffusion time. We will see in a bit. And because of this trace, you can do an expansion and get this very interesting symmetric formula. You have VLO, the L's eigenvector, and you consider J's J's block, and you do the inner product, and so on. An interesting thing is you see this is II and the JJ. So this suggests the following possibility to achieve an embedding of points. So we take this point, this fact into account, and we define a vector diffusion map. That is, you have a VT, you just map the ith point into lambda L, lambda R raised to power T, and you just take one part into it, such that the Hilbert-Schmidt's norm of S tilde 2 Tij is actually inner product of VTI, VTJ. So this is directly from this expansion, you define vector diffusion map. And once you have vector diffusion map, you can just like before define vector diffusion distance. That is a VTI and VTJ. You just evaluate their L2 distance after the embedding. That's called vector diffusion distance. So pictorially, what you have is you have a graph connection Laplacian, like before, and you have vector diffusion maps VT. You map everything to another Euclidean space, and you get VTJ and the VTI, and if you evaluate their Euclidean distance, that is vector diffusion distance. That's what we do. And then once we have a new affinity, then you can use this new affinity to do whatever you like. For example, k-means, group, whatever. There are many things you can continue. Okay. So this is just a new way to define metric, and we can show that this metric is actually robust to noise. When we work with a manifold setup, it will recover geodesic distance, etc. And those are what we will discuss in a bit. So before closing today's lecture, let's take a quick look about relationship with diffusion map. Suppose G is SO1, that is SO1 is 1, just like what we did before. Okay, then the diffusion map or eigenmap is a subset of vector diffusion map. And why so? Recall what is diffusion map. Diffusion map is defined as mapping the i's component to lambda LT and the V LOI. That is what we do. And remember, when the group is 1, everything is just like graph Laplacian. Exactly like graph Laplacian. And if you still use the same data, the same connection to define vector diffusion map, then that is what you get. And you see, what is the relationship in between them? This is just like an inner kind of cross turns, all quadratic cross turns of diffusion maps, isn't it? And if you want to connect them further, you see the first eigenvalue is trivial, the first eigenvector is trivial of the graph Laplacian. So the first coefficient is always constant. So what you can see is diffusion map is like vector diffusion map, but you only restrict it on R is 1. That is when R is 1 and when you really take 1, the trivial eigenvector and eigenvalues. Then vector diffusion map is a superset of diffusion map. Diffusion map is a subset of vector diffusion map. That is the relationship. Okay, so when you really have a trivial connection, the diffusion map and vector diffusion map, they are related. They are. But what is a relationship? A relationship is a subset. And the one question you can ask is, what about if you really consider, even if G group is SO1, what benefit can you get from vector diffusion map? Then we do not have an answer at this moment. Okay, so yeah, that is what I mentioned. So yeah, I think that is it.